Hi, I'm Alex. I work for a group at Apple called Tools Foundation. Normally we get to do fun stuff like operating systems and compilers, but this year we got to do something a little different. We built a game called swiftshot. Some of you may have seen it earlier today, and you might have played it downstairs. But the important part is that swiftshot is a showcase of some of the new functionality in ARKit. ARKit 2 is now available on hundreds of millions of devices, providing a platform for engaging AR experiences, and you're able to reach the widest possible audience with that. There's no special setup. Just point the device's camera at a surface and start playing. It's integrated into iOS, first-party and third-party engines like SceneKit and SpriteKit, as well as third-party ones like Unreal and Unity have full integration at this point. A little agenda for you. First, we're going to talk some game design principles for augmented reality, a few of the things we learned along the way. We're going to go deep into the internals of the game, and in particular, we're going to cover world map sharing, which is a new feature in ARKit 2, and we'll also talk about networking and physics and how we made that work. First, let's take a deep look at the game. So let's talk a little bit about designing games for augmented reality. Above all else, gameplay comes first. You should ask yourself, if you're designing a game, would this game be fun and enjoyable if it were just 1970s graphics or plain flat-shaded gray cubes? It's worth prototyping with those kinds of artwork and get that gameplay down. Because if it's fun with those boring gray boxes, it's going to be fun when you add all the graphics and sound later. You should spend time refining that, and don't convince yourself that if I just add another 5% better graphics or that one feature, that the game's suddenly going to be fun. Because, there's a wasteland of games out there that were never fun from the get-go. So try not to fool yourself. Let's start with the gameplay. Keep games short. You're looking for a typical mobile experience still. Easy in, easy out. You want to keep a variety of content so that it's fresh. Avoid mental fatigue on the part of the player of repeating the same thing over and over again. One of the things we learned is that spectating the game turned out to be just as fun as playing it. Sitting there on the sidelines and watching like it's a sporting match going side to side, that's just a really enjoyable experience. Something to think about. Now, games are a key form of social and personal interaction. Augmented reality can offer a kind of personal touch that you might have had before playing like a traditional card game around the table with older relatives. But now you have technology to help along the way. It isn't enough to just take a 3D game and put it on a table in front of you. With augmented reality, you know how the device is positioned. You also know a little bit about the user's environment, and you should try to take advantage of that in the game and make experiences that are really for augmented reality first. Your device can be used as a camera to look inward at an object of focus. In this case, this is a 3D puzzle game where we're looking to repair a broken vase. We can look all around it, figure out what piece goes where, and do our best on the repairs. In swiftshot, we took a similar concept. The focus is the table you're playing on, and you can walk around it. But the table isn't just the tracking surface for augmented reality. It's an integral part of the gameplay. The height of the table is actually significant, and as a result, you'll see in the game that there are slingshots at different heights on tops of stacks of blocks in order to give you better shots or take advantage of the player dodging and weaving a little bit. Another possible principle is your device is a camera you use to look around you. In this case, we're looking for unicorns hiding out in the wilderness. We're taking pictures of them. It's just around you, not inward. Your device can also be a portal into an alternate universe. You don't need to see what the camera sees directly. The environment can be entirely replaced. Laws of physics can be bent or completely changed. Whatever you need to do to make it fun. In this case, we're able to see the stars even though it's bright daylight. Also, your device can be the controller itself. You're able to fuse yourself with the virtual world using the device as the controller. In this example, we're sort of magnetically levitating blocks and placing them in the sorting cube. That's the focus of the interaction in swiftshot. You want to encourage slow movement of the device. That gives the best images to the camera without motion blur, and it can do the best job of tracking. And despite how thin and light these devices are, waving them all around at arm's length turns out to be a little bit tiring. So you're looking for slow and deliberate movements. You want to encourage the player to move around the playfield. In this case, our shot of the enemy slingshot is blocked by those blocks. So we have to move over to another slingshot to clear the obstruction. Control feedback is important for immersion. In swiftshot, we give feedback using both audio and haptics. There's a variety of dynamic behavior in the stretching band sound and haptics on phones to give you that feel that you're doing it. We'll talk a lot more later about the dynamic audio. So next, I'd like to bring up David Passage, who will go deep into the details of swiftshot. Thank you. David?
Thank you, Alex, and hello, everybody. I just want to echo what Alex said. The response that we've seen from people here at the show to swiftshot has been really amazing, and it's been gratifying to see some people already downloading it, building it, and altering it from the sample code. So thank you for that. We're really excited about that. I want to talk by talking first about the technologies we used in building swiftshot. The first and foremost is ARKit, which lets us render the content into the physical world around the players, immersing them in the experience. We use SceneKit to manage and draw that content, using advanced 3D rendering and realistic physics for fun gameplay. Metal lets us harness the power of the GPU devices. It came into play both within SceneKit for the shading and rendering, and also for the flag simulation, which I'll talk about a little later on. Gameplay Kit provides an entity component architecture for our game objects. It let us easily share behaviors between objects in the game. Multi-peer connectivity provides the networking layer, including discovery of nearby devices and synchronization, and encryption as well. AV Foundation controls both the music for atmosphere and the sound effects for the devices, really giving you that immersive experience. And lastly, we built the entire application in Swift. Swift's type safety, performance, and advanced features like protocol extensions let us focus more on the gameplay and worry less about crashes and mismatched interfaces between code layers. Those are the iOS technologies we used. I'll talk about how we used those as we implemented several of the features of the game, establishing the shared coordinate space, networking, physics, asset import and management, flag simulation, and the dynamic audio. We'll start by talking about setting up a shared coordinate space. The key in the experience is having the players see the same objects in the same places on both devices. To do that, we have to have a shared coordinate space. allowing them to talk about locations in the world in the same way. ARKit provides a number of features you can use to set this up. In iOS 11.3, we introduced image recognition, allowing your apps to recognize images in the world around you. Now in iOS 12, we're adding 2 additional technologies, object detection and world map sharing. Both image detection and object detection let you add content to things the user sees in the real world, but they require you to have pre-recorded those objects for later recognition. You saw that in the keynote during the Lego demo, recognizing built models and adding content. For this game, we wanted to enable users to play anywhere with a table, such as a cafe, their kitchen, and so forth. World map sharing is how we did that. You can also apply this technique to applications besides games, like a fixed installation in a retail environment or a museum. In the game room downstairs, we use iBeacons so devices know which table they're next to and can load the correct world map for that area. That really makes the experience magical. One of the features of swiftshot you may have used if you built your app yourself is the ability for players to place the game board in the virtual world. At the tables downstairs, we're using preloaded maps, but here's an example of building your own board and placing it in the virtual world. This is how that works. As you saw in the video, you start by scanning the surface, letting ARKit build up a map of the area. You can then serialize that map out as data and transfer it to another device. The target device then loads the map into ARKit and uses it to recognize the same surface. At that point, we now have a shared reference point in the real world, and both devices can render the game board into the same place in that world. The first step in the implementation is getting the world map from the AR session on the first device. That's a call to a new API in iOS 12 on AR session, get current world map. It builds an AR world map object from the session's current understanding of the world around you, and then returns it in an asynchronous callback. We then use NSKeyed Archiver to serialize it out to a data object. You can then save the data or send it over the network. Once you have that data object, you next have to decide how to get it from one device to another. For ad hoc gaming, like you saw in the video, swiftshot uses a peer-to-peer network connection, which we'll get into more detail on shortly. When the second device joins the network session, the first device serialized the world map and sent it over the network. This is great for casual gaming situations, allowing users to set up anywhere they can find a surface to play on. For the gaming tables downstairs, we used a different approach. We spent some time during setup for the conference recording world maps for each of the tables, ensuring that we could localize to that shared coordinate space from multiple angles. Each table has its own unique characteristics, as well as slightly different lighting and positioning. We then saved the files to local storage on each device. Since the devices in use are managed by our conference team, we're able to use mobile device management to make sure that the same files were present on every device in the game. To make the solution even more seamless, you can use iBeacons on each table. By correlating the identifier of the iBeacon with particular world maps, each instance of the swiftshot application can load the correct world map automatically. Now, if you're building a consumer application, you can also use things like iOS's on-demand resources or your own cloud sharing solution to share world maps between devices. This would allow you to, for instance, select the correct world map for a particular retail location somewhere out in the world. There's really a lot of possibilities here to tailor a user's experience and really build something great. So those are a couple of ways to get that world map data from one device to another. Let's talk about how you then load it on the second device. In this case, we use NSKeyed Unarchiver to blow up that world map again from the data that we received. We then build an AR world tracking configuration and add the world map to that configuration object, setting up the way we want. And then lastly, we ask the AR session to run that configuration, resetting any existing anchors and tracking. ARKit on the target device then starts scanning the world around you, correlating those feature points from the original map with those that it sees there. Once it's able to do that, you've got that shared coordinate space. Both devices have 0, 0, 0 in the same place in the real world. So a quick word about privacy with world maps. In the process of recording the world map, we take into account features of the world around you, physical arrangements of objects, and so forth. While it doesn't include geographic information like latitude and longitude, and thus your application doesn't need to ask for location permission to use ARKit, it may include personally identifiable information about the user's environment. So we recommend that you treat a serialized world map the same way you would any other user-created private data. This means that you want to make sure that you're encrypting it both at rest and when moving across the network. You may also want to let your users know if you're planning to save that world map information for an extended period of time, past a single session of your application. In swiftshot, we're able to take advantage of iOS's built-in encryption for encrypting the data while at rest. I'll talk next about how we did the networking for encryption on the networking. Now, in addition to setting up a shared coordinate space, for swiftshot, we need to tell the other device where the user has chosen to locate the board. We use an AR anchor to do this. When you create an AR anchor, you provide a name as well as position and rotation information as a 4x4 transform. ARKit can then include the anchor in the AR world map we generate and serialize out, and then so we can transfer that board information to the other device. Now, the system AR anchor class just has the name and the orientation when you create it. We can look up the anchor that we're interested in by name on the other side. For our application, though, we need to include some additional information for the other device, and that's the size that the user chose for that board, deciding whether they're playing on a small tabletop and surface, or they want to blow the board up to be the size of that basketball court. We thought about adding that to our network protocol alongside the world map, but then we came up with a better solution. We created a custom subclass of AR anchor that we called board anchor, and added that information to that class, the size of the board. We then made sure that we implemented the NS coding required classes, or override them, to include that information when the object is serialized out. Now, the information is included directly within the world map when we transfer it over to the other device. This makes it very easy and straightforward. One thing to keep in mind, and this bit us for a little bit, when you use Swift to make a subclass like this, when you serialize it out, the name of the module, or the name of your application, is included in the class name. This is something to be aware of if you're planning to move world maps between different applications. And NSKeyed Archiver can help you accommodate that. So that's world map sharing. That's a new feature in iOS 12. We're really looking forward to seeing what everyone can build with that. Next, let's talk about the networking we built into the game. We used iOS's multi-peer connectivity API, which has been in the system since iOS 7, in order to do this. Multi-peer connectivity allows us to set up a peer-to-peer session on a local network, allowing devices in the session to communicate without going through a dedicated server. Now, in our application, we designate one of the devices as the server, but that's something that we did for our application. It's not inherent in the protocol. Encryption and authentication are built into multi-peer connectivity. In our case, we didn't use authentication because we wanted a very quick in and out experience, but we did use encryption. We found that turning on encryption really provided no performance penalty. So there's either in network data size or computation. So there's really no reason not to use it. Multi-peer connectivity also provides APIs for advertisement and discovery. We use this to broadcast available games and allow players to select a game to join. So here's how we get that session set up. First, on one device, the user decides to set themselves up as a host for the application. They scan the world, place the game board within that world, and then the device starts a new session, multi-peer connectivity session, and starts advertising it to other devices on the local network. A user on the other device sees a list of available games. When he selects one, his device sends a request to join the existing session. Once the first device accepts the request, multi-peer connectivity sets as a true peer-to-peer network. Any device in the network can send a message to any other device in the network. In swiftshot, we designate the device that started the session as the source of truth for the game state. But again, That's the decision we layered on top of the networking protocol. It's not inherent in multi-peer connectivity. Once the session is set up, multi-peer connectivity lets us send data between peers in 3 ways: as data packets, as resources, file URLs on the local storage, and as streams. Data objects can be sent broadcast to all peers in the network, whereas resources and streams are device to device. In swiftshot, we use the data packets primarily as a way to share game events and also the physics state. We'll talk about that later on. And then we use the resources to transfer the world map. Ended up, we didn't need streams for our application. Under the covers, multi-peer connectivity relies on UDP for the transport between devices. This gives a low latency, great for applications like games. Now, UDP inherently doesn't guarantee delivery, so multi-peer connectivity lets you make that decision and specify whether a particular data packet is to be sent reliably or unreliably. If you choose reliably, multi-peer connectivity takes care of the retries for you, so you don't have to worry about that in your code, even when you're broadcasting to all members of the session. Now that we have a networking layer, we need to build our application protocol on top of it. Swift enums with associated types make this very easy. Each case has a data structure around it, ensuring type safety as information moves around the system. Some of those can be further enums. So for an example, game action includes things like a player grabbed a catapult, a projectile launched, and so forth. The physics sync data is a struct, and I'll talk more about how we encoded that later on. Again, Swift makes this very easy. For structs, if all the members of the struct are codable, then all you need to do is mark that struct as codable, and the Swift compiler takes care of the rest, building all the infrastructure needed for the serialization. Swift doesn't do that for enums, and so we ended up implementing that ourselves, implementing the init and encoding methods from the codable protocol to make that work. Serialization then is very easy. Just build a property list encoder and have it encode the object out for you. We can then send a data packet within the multi-peer connectivity session. Now, a reasonable question here might be, how's this going to do in size and performance? Binary property lists are pretty compact, and the encoder is pretty fast. But sometimes, this implementation in many ways is optimized for developer time, which is sometimes your most precious resource on the project. Now, we ran up against some of those limitations as we started to build the next feature, and we'll talk about how we overcame those. So let's talk next about the physics simulation in the game. For a game like swiftshot, physics is really key to create a fun interaction. It comes from the realistic interaction between objects in the game. It's a really great experience to take that shot, bounce it off an object in the game, and take out the opponent's slingshot. And that really comes from the physics simulation. We used SceneKit's built-in physics engine. It's integrated with the rendering engine, updating positions of the objects in the scene automatically, and informing us of collisions using delegation. In our implementation, we decided that the best approach was for one device in the session to act as the source of truth, or server. It sends periodic updates about the physics states to the other devices in the network using that multi-peer connectivity broadcast method. Now, the other devices also have the physics simulation on. That's because we don't send information about every object in the game, only those objects that are relevant to the gameplay, such as the blocks, projectiles, and catapults. Things like simulating the swinging of the rope in the sling, particles, and so forth, those are just done locally on each device, since it's not critical to the game that they be in the same place on every device. Now, one of the things that we discovered is when we were doing this was that the physics engine responded very differently depending on the scale of the objects. And so the physics simulation thinks the objects are about 10 times the size as you would see them in the real world. We found that gave the best gameplay experience and the best performance. We had to tweak some of the laws of physics to make that look right, but when you're building a game, if it looks right and feels right and it's fun, then it is right. Now, to share that physics state and make sure everything looked right, we need to share 4 pieces of information: the position, the velocity, the angular velocity, and the orientation. That's a lot of information about every object in the game. So it was vital that we minimize the number of bits actually used. I'll walk you through that using position as an example. SceneKit represents position as a vector of 3 floating point values. This is the native format and gives the best performance for calculations at runtime. However, there are really more bits than necessary to specify the object's location. A 32-bit float has 8 bits of exponent and 23 bits of mantissa for a range of plus or minus 10 to the 38th meters. That's way more than we need for this game. So because the physics simulation thinks our table is 27 meters long, we said, 80 meters is going to give us plenty of buffer space around that on either side. When recoding that, then, we're able to eliminate the sign bit by normalizing that between 0 and 80 meters, even though our origin is at the center of the table. Now all values are positive. We then scale that value to be in a range of 0 to 1. That way we don't need the exponent information as inherent in the protocol. And then lastly, we take that and we scale it to the number of bits available, so that all ones is a floating point 1, and all zeros is the floating point 0. This gave us millimeter scale precision, which we discovered was really enough to achieve that smooth synchronous appearance in the game. Now, we did a similar technique for all the other values that you saw, the velocity, angular velocity, and orientation. Tailoring the ranges and the number of bits for each to really make sure that we transmit the information using the minimal amount of data. Overall, we reduced the number of bits for each object in more than half. Now, even though we've compressed the numbers, property lists still have a fair amount of overhead for the metadata around it, sending each field by name. Instead, there's no reason for that. We all know what these objects are. That's not information we need. So to do this, we implemented a new serialization strategy, which we call a bit stream. Bit streams are designed to pack the information into as few bytes as possible while providing fast serialization and deserialization. Now, our implementation is purpose-built for communicating binary data with low latency in an application like this. Strategy like this wouldn't work well for data that needs to persist or data where you need to keep track of the schema and watch it changing over time. But for an ephemeral application like this, it was just the thing. To help implement this, we created 2 protocols, bitstream encodable and bitstream decodable. Combine those and you get bitstream codable. And then we took that and marked all the objects that we needed to serialize using that protocol, helping us to get the implementation. That includes both our own data objects and the objects we use from the system, such as the SIMD floating point vector type. So here's the implementation of compressing floats. The compressor is configured with the minimum and maximum range and the number of bits we want it to use. It clamps the value to the range and then converts it to an integer value for encoding using the specified number of bits. Each component for each object in the scene is compressed in this way. We also use an additional bit at the front to tell if an object has moved since the last update. If it hasn't moved, we don't resend that information. So let's go back to our action enum with the 3 different actions and talk about how we apply bitstream to this. For regular codable, if you're doing your own serialization, you specify encoding keys for enums for the different cases in the enum. For bitstream, we used integer values for this rather than string values. And then in our encoding method, we're able to then append that value first, followed by the data structure associated with that case of the enum. Now, if you look at this code, though, there's kind of a pitfall here. We know that this case has 3 different cases, and so we only need 2 bits to encode it. But what happens when we add another case, 4 bits, 4 cases, we're still fine. We add that 5th case, now we need to go through and change that so that every time we do this, we're using 3 bits instead of 2. Now that's kind of tedious. This code's a little bit repetitive, and there's stuff that can go wrong there. If we don't remember this, we're just going to end up in a bad place. So we took a look at this and figured out that there was a way that Swift can help us do this. So we used a new feature in Swift 4.2, which is case iterable. We added that protocol compliance to our enum type. When you do that, Swift adds a new static member of the type called allCases, containing each of the cases in the enum. That lets us automatically get a count of the number of cases. We then added another extension, this time on the raw representable type, which all enums with number types like that conform to, where it's case iterable and where that number is a fixed width integer. And in this, we get to automatically take those number of cases and figure out how many bits it takes to represent all those cases on the wire. Lastly, we added a generic method on the writable bitstream type, allowing us to encode that enum. It appends things of that type, and it uses that new static property to figure out the number of bits that are needed to use. Now our encode method is much simpler. We just use append enum on the proper coding key for each, and Swift takes care of the rest. When we add more cases to the enum, the bit field expands automatically. If we remove cases, it contracts automatically. We don't have to worry about it. So how much faster and more compact is bitstring encodable? We ran some tests using XCTest support for performance testing, using a representative message in which we send information about object movement. The results were pretty impressive. 1/10 the size, twice as fast to code, 10 times as fast to decode. Now, when we're talking about going from 75 microseconds down to 6 microseconds, that seems like small potatoes. But there's around 200 objects in the game, and we want to do this very frequently to make sure the game remains smooth for all participants. By using this encoding format, we were able to do those physics updates at 60 FPS, ensuring that you get a smooth experience for everyone in the game. Now, I've talked about this. We did some things with Codable and some things with bitstream Codable. That you could have a problem there, because we're encoding things two different ways. And that means now we need to have two different code paths through our application. Swift helped us out again and let us figure out how to combine them. We then added constrained extensions so that anything that is codable and bitstream codable, we provide default implementations of the bitstream encodings. And then we just go ahead and use a binary plist encoder to encode to data and stuff it in the bitstream. And then any struct that is codable, we can just add that by marking it as bitstream codable. Now, this implementation then is not as fast as and compact as if we went forward and made everything bitstream codable directly, but we discovered we didn't need to do that for every object in the game, only the most frequent messages. This let us really move quickly and keep iterating on the game. So that's how we did the physics. Next, I want to talk about how we dealt with the assets for the game levels. And this is a question that a lot of people asked us downstairs. The assets include the 3D modules, the textures, the animations, and so forth. So we have some technical artists here in Apple, and they use some commercial tools to build the visuals for the games, the blocks, the catapults, and so forth. They then exported those assets in the common DAE file format. We're looking forward to the commercial tools supporting USDZ, but for this game, they weren't quite there yet. We then built a command line tool in Swift that converts the objects from DAE into SceneKit files using the SceneKit APIs. Because SceneKit provides the same APIs on both iOS and macOS, we're able to run this tool as part of our build process on macOS and then include the SceneKit files directly in our iOS build of the application. We structured the data so that each individual type of block is in its own file. And then for each levels, we combine those blocks together. This let us iterate on the appearance and physics behavior of each individual block, and then pull them all together for those levels, and iterate on gameplay design. Try out some of the different levels that you'll see if you look in the source code for the application. To further optimize for different distances, SceneKit supports varying the assets used based on the level of detail required. Nearby objects use more polygons and more detailed textures, while faraway objects use fewer polygons and less detailed textures. This really optimizes the rendering of the scene. However, we still want the gameplay to stay consistent, and so we specify the physics bodies separately. SceneKit provides a number of built-in physics body types, such as cube, sphere, cylinder, and if you use those, you really get the best performance. If you don't specify one, SceneKit will build a convex hull automatically for you, and that works, but it can be a lower performance implementation. By adding these objects where they were available and where they made sense, we really sped up the performance of the game. So here's some examples of the finished product. First one is one of the blocks from the game, in this case a cylinder with textures for a great wood grain look. Next is a slingshot with a sling at idle. We add the team colors at runtime using shaders and built some custom animation for the sling's motion during gameplay. Lastly, we included some extra assets that didn't get included in the gameplay. Even though we had to sacrifice them, we want you to have them and use them in your own sample code. So one of the other fun things we included is this flag animation. It really improves the immersion in the game environment. We wanted a realistic wind effect on this. Now, we could have used a cloth simulation out of the physics engine, but instead, we decided to use the GPU and do it with metal. We started with a SceneKit asset built by our technical artist. To get the Apple logo on the flag, we applied a texture at runtime. Then we built a Swift class around a metal device. The Swift code builds a metal command queue and inserts information from the state of the game, such as the direction the wind is blowing. That command queue is running a custom metal compute shader. That comes from legacy code built in C, but because metal is based on modern C++, it was a very easy conversion to make. We then also run another compute shader to compute normals for the surface, so we can get a great smooth flag look without a huge number of polygons in the scene. And it really makes the flag look amazing. Each frame, the shader updates the geometry of the mesh to its new position. By taking advantage of the GPU in this way, we get a great effect without impacting the main CPU. So lastly, I'd like to talk about the audio implementation in swiftshot. Audio can make any game even more immersive and engaging. We knew we wanted to provide realistic sound effects, positioned properly in the world for that really immersive experience, and giving the user great feedback on how they're interacting with that world. We also wanted to make sure it was fast and pay attention to how much adding the audio would add to the size of our app. So we came up with what we think is a great solution. We created a few representative sound samples using some toys we borrowed from children of people on the team. We then recorded those and used those to combine them into a AU preset file and use those to build a custom MIDI instrument in AV Foundation using AV Audio Unit MIDI instrument. That made it easy to quickly play the right sound at the right time in response to user inputs and collisions in the game. We didn't just play the sounds as is. To give good feedback to the user, we pull back on the slingshot. We vary the sound in a couple of ways. We change the pitch based on how far back they've pulled the slingshot, and we vary the volume based on the speed as you pull that. And we do that at runtime by selecting the right MIDI note and then using some additional MIDI commands to alter that sound before we play it. So let's take a listen. And this is a little quiet. Now, we also wanted to make sure that when you're using the slingshot, we also give users some audio feedback as to whether or not they're within range of the slingshot and whether or not they've grabbed that. And those were the little beeps you heard at the start. Because those are UI feedback for the users, those sounds only come out of the device that the user is using to interact with the slingshot. However, we also want everybody else in the game to know what's going on with the slingshot, whether someone else is pulling something or something like that. But we want one of those to be quieter. So we use positional audio, so that if my opponent across the table is pulling their slingshot, I still hear that sound from my device, but it's quieter and positioned correctly in the world. For colliding blocks, we took a similar approach, but slightly different. We really wanted a cacophonous effect. And the blocks are generally not near any one player. So again, using the positional support from SceneKit really made this sound great. Each device makes sounds separately without worrying about synchronizing across devices because we want it to be cacophonous, blocks smashing about. Again, we used a custom MIDI instrument to take a small number of sounds and vary them, in this case varying the attack rate based on the strength of the collision impulse coming from the SceneKit physics engine. These sounds, again, are localized in 3D coordinates based on the device's position in the scene, so collisions on the far end of the table are quieter than those at your end. Let's take a listen to this. One more shot. There we go. Great. So we want to share one more little trick that we discovered as we were working on this. In the process of setting up those sounds, we discovered that we needed to have a script run at runtime to do some file name path conversions on the property list for the EAU preset. We found that we're able to build that tool using Swift, but set it up as a command line tool. You notice at the top of this, the traditional Unix shebang style statement at the top of the script that tells your shell to fire up Swift to run this. By doing this, we can then treat Swift as a scripting language. You can develop one of these by using a Swift playground to work with your code interactively and make sure that you've gotten it right. Once it's ready, just save it out to a file, add the shebang line to the top, and make the file executable in the file system. Now you've got a command line tool that you can use either outside the application or in Xcode using a run script phase. It's very easy, and it really gives you access to all the system frameworks. In this case, we're able to edit the plist directly. It's a really great technique, and we hope that you'll be able to take advantage of it. So today, I hope you've seen how AR provides really new opportunities for engaging games and other experiences. We encourage you to design with AR in mind from the start. And remember that for games, the play is the thing. You can't sprinkle fun on top at the end. We really hope that you'll download the swiftshot developer sample code and use it to guide you as you build your own apps. And we're planning to update that with each subsequent seed of iOS 12 as we go to the release. And finally, if you hadn't had a chance yet, we hope you play swiftshot with us downstairs in the game room. For more information, there's an AirKit lab immediately after this session and a get-together this evening. I'm also happy to announce that for those of you here at the conference, we're going to have a swiftshot tournament this Friday from noon to 2. So we hope you'll join us for that. Thank you very much.